Now we've seen a taste of how to apply this theorem. Let's actually go about proving it. Okay? So this is from the May-June paper from 2018, and the first question is asking you to prove this theorem that states that a line drawn parallel to one side of a triangle, right, divides the other two sides proportionally. Okay, so we're going to have our proof. We are given triangle XYZ, okay, with K on XY and L on XZ, such that KL is parallel to YZ. Okay, then you are required to prove that XK to KY is in the same proportion as XL to LZ. Right. So once you've stated that, you can now go on to your proof. But for this proof, you need to start off with a construction. Okay, so you're going to tell them you need to draw height, H, right, from K to base XL and draw height K. Let's make this K a little bit different. K from L to base XK, right? So remember from primary school, you were taught that the base of a triangle can be any side of the triangle. It doesn't necessarily have to be this bottom side. You can choose the base to be this, and then the perpendicular distance is from that base to the opposite vertex, right? So that's just information that you need to remember from primary school, right? So this is the construction. And lastly, you need to say join, okay, YL and KZ. Right. So let's draw all of these things in. And these two triangles are connected by the same base. So they have the same base, KL, and they are between the same parallel lines, right? Therefore, they have equal area. Okay, they have equal areas because they have equal heights, right? So that's one of the information that you're going to need to know in order to construct this proof, right? And then another thing that you need to know is that when you have triangles that have the same altitude, right, then the areas of those triangles are proportional to their bases. Okay, so in this diagram, the triangles that have the same altitude is, if you look at this big triangle X, Y, L, okay, if you look at that triangle, the perpendicular height for that triangle is K, okay? And how many triangles are within this big triangle? You have the triangle XKL, right? So you have this triangle, XKL, But you also have the triangle KYL, which is at the bottom. Okay, and its height is, for both these triangles, they have the same height, K, right? And then on the other side, you also have, if you look at the triangle XKZ, right? Its perpendicular height is H, right? And that is the perpendicular height for triangle XKL, right? And KLZ. So once you can see that, you'll be able to construct this proof. So okay, firstly, we're going to say, let's look at the area of triangle XKL to the area of triangle KLY. Okay, so remember that was the triangle that I highlighted initially in green. Okay, so this big triangle that contains two triangles, XKL, right, and KYL, right. Okay, let's look at this ratio first. Okay, so remember, for these two triangles, their height is K. So you're going to have half times the base for XKL is XK, right, times its height, which is K, right? Divided by the area of triangle KLY is half times the base is KY times its perpendicular height K. Right. So now you can see that the halves will cancel each other out and the height will cancel each other out. Right. This is then equals to XK over KY. Right. So now what we're going to do is, now we're going to switch over and look at the other triangle that has the same altitude. If you look at the ratio of the area of triangle XKL to the area of triangle KZL, right? These again have the same altitude. This time their altitude is H, right? And because they have the same altitude, the ratio of their areas is going to be proportional to their bases. But we're going to have to prove that, right? So if you look at XKL this time the base being XL, perpendicular height is H. So you have half times XL times H divided by 1/2. For this triangle KZL, that one over there, okay, its base is LZ and its perpendicular height is also H, so times LZ times H. Again, the halves will cancel and the height will cancel, leaving you with XL over LZ. Right. So now, if you see so far, we've managed to get the ratios which are needed. We have XK over KY. We also have XL over LZ. Right. Now the only problem is that we need to prove the bottom of these fractions, so the area of triangle KLY and the area of triangle KZL, we need to prove that those two are equal in order for us to conclude that these ratios are equal. And remember, those two triangles are the ones that I told you in the beginning. They share a common base, KL. Right. Okay, so we're just going to state that. But the area of triangle KLY is equals to the area, area of triangle KZL. And the reason for this is because they have the same base, KL, right? And they're between the same parallel lines, KL parallel to YZ. Right. So that's the reason for us saying that these areas are equal, right? Now, because the top triangle is exactly the same, it means that these two fractions then are equals to each other. So therefore now we can say that the area of triangle XKL to the area of triangle KLY is equals to the area of triangle XKL to the area of triangle KZL, right? Therefore, XK over KY is equals to XL over LZ, right? And then thus you have now proven your theorem. Okay. So now that we've proven this theorem yet again, let's look at another example on how to apply it. Okay. So over here they say that in triangle RST, F is a point on RS, H is a point on RT, okay, such that FH is parallel to ST. Okay, you're further given that RF is equals to 2x minus 10, Fs is equals to 9, RH is equals to 4, and HT is equals to x minus 2. Right. Now the first question says, question 9.2.1 says we need to determine, giving a reason, the value of x. Okay, so we can see quite clearly that x is part of the lengths of these triangles, of this triangle, and because we've already proven the theorem, you don't have to prove it again, right? You can go straight to the conclusion of the theorem that states that if you have a line drawn parallel to one side of the triangle, the conclusion is that this line, if H, divides the other two sides of this triangle in the same proportion. Okay, so for question 9.2.1, you immediately state that F to Fs is in the same ratio as RH to HT. And the reason for this is because we have a line drawn parallel to one side of the triangle. Okay. Now we just have to substitute. Okay. RF is given to us as 2x minus 10 divided by Fs is 9. RH is 4. T is x minus 2. Okay, now we can cross multiply, so we have 2x minus 10 into x minus 2 is equals to 9 times 4, which is 36, right? Then we're going to fill out this bracket, which is going to give us 2x squared minus 4x minus 10x plus 20 is equals to 36, right? That leaves us with 2x squared minus 14x. 20 minus 36 is minus 16 is equals to 0. Our next step can be to remove a common 2 from all of these terms. So we'll be left with x squared minus 7x minus 8 is equals to 0. Dividing both sides by 2 will leave us with x squared minus 7x minus 8 is equals to 0. This can be factorized into x plus 1 into x minus 8 is equals to 0. Therefore, x is equals to minus 1 or x is equals to 8. And because we're dealing with the lengths of a triangle, obviously if you substitute an x of minus 1, for example, if you substituted minus 1 over here, you will have minus 1 minus 2, which is going to be minus 3. Already that is not applicable because we can't have negative lengths. So therefore x is equals to 8 is our only answer for the value of x. Right. Now for question 9.2.2, it says determine the ratio of the area of triangle, so RFH, to the area of triangle RST. Okay, RST. Okay, so you're looking for the ratio of the small triangle to this big triangle. Okay. Okay, so remember I told you previously that when you have two triangles that have the same height, okay, equal height, then the ratio of their areas will be proportional to their bases, right? Unfortunately, we cannot apply that theorem over here because they're asking us to find the ratio of the area of the small triangle to this big triangle. Those two things don't have the same height, okay, obviously. So we are not going to be able to use the proportion of their bases, right? However, we can go back to something else that we know about area. Okay, so just recall from trigonometry, right? We stated that for any triangle ABC, right, that is not a right angled triangle, the area of that triangle by the area rule, okay, is equals to a half times CB times the sine of the included angle. Okay, so it would be this side times that side times the sine of this included angle. Okay, so that is exactly what we're going to apply in order to solve this question. Okay, so let's look at the area of the small triangle RFH. Okay, this is equals to, from this area rule, it's going to be a half times, let's choose the side RF times RH times the sine of the included angle would be R. Okay, we need to divide this by the area of the big triangle RST. Again, this is going to be 1/2 times RS times RT times the sine of the included angle. Again, it's exactly the same R. Okay, so I chose to use R as the included angle because that's the common angle to both of these triangles, and thus that will allow me to cancel out the sine of R. Then I don't have to worry about computing it. Okay, so now we're left with RF. Okay, so RF over there is this. If you substitute 8 over there, remember we solved that x is equals to 8. You'll have 8 times 2, which is 16, minus 10 will give you 6, right? On the other side, our h is equals to 4 divided by rs is this full length. Okay, so remember we have a 6 over there, so 6 plus 9 is 15. And then for RT, if you substitute an 8 over here, you have 6 plus 4, which is 10. Okay, then if you substitute, plug all of this into your calculator, you get that the ratio of the area of RFH to the area of triangle RST is equals to 4 over 25. Okay, and that's basically our second example done on how to apply the proportionality theorem.